All right, so here's the plan. First, we'll get a handle on what the cracking point really is. Then, we'll get our hands on the formulas we need to figure it out. We'll run through a case study with a simple rectangular beam, then tackle a trickier T-beam. After that, we'll do something kind of cool and flip it over to see what happens. And we'll wrap up with why that first little crack is such a huge deal.
So you know how concrete beams have all that steel rebar inside? Well, for a while that steel is just hanging out. It's not doing anything yet. The beam is acting like one solid block of concrete. Our mission, really, is to figure out the exact limit of that state. You know, the precise moment the tension gets to be too much and the concrete just can't take it anymore on its own.
Now, finding this cracking point isn't guesswork. Nope, it's all about the math. And to do the math, we need 3 key formulas. You can think of these as the essential tools in our engineering toolkit for predicting exactly when things are about to get cracky.
All right, so everything we're about to do, it all boils down to finding this one magic number. It's called the cracking moment, or MCAR. And that number is the answer to our big question. What's the maximum bending force this beam can handle before that first, tiny, but super important crack shows up? It's the beam's breaking point.
Okay, let's open up that toolkit. First, we've got bending stress, F equals my over Ig. This one tells us how much stress is happening at any given spot inside the beam when you bend it. Super useful. Next up is the modulus of rupture, Fr. Now this is the concrete's actual strength, like how much you can pull on it before it snaps. And finally, the star of the show, the cracking moment formula. MCR equals Fr times Ig over Yt. This is the one that pulls everything together and gives us that magic number we're after.
All right, enough with the theory, right? Let's get our hands dirty. We're going to take our new toolkit and use it on a real-world example, a simple, everyday rectangular beam. Okay, here it is, our test subject. It's a 12-inch by 18-inch rectangular beam. The concrete itself has a strength, what we call F'C, of 4,000 psi. So, here's the question. If we put a bending force, a moment, of 25 foot kips on this thing, is it going to crack?
Okay, first things first, we need to figure out how much this beam resists being bent. That property is called the gross moment of inertia, or Ig. For a simple rectangle, the formula is pretty clean. Ig is just 1/12 times the base times the height cubed. So we plug in our dimensions. The base, b, is 12 inches. The height, h, is 18 inches. That gives us 1/12 times 12 times 18 to the power of 3. Punch that into the calculator, and we get 5,832 inches to the fourth.
Okay, we have its resistance. Now let's see how much stress that 25-foot kip moment is actually putting on the beam. We'll use our bending stress formula, F equals my over Ig. Now, quick conversion. 25-foot kips is the same as 300,000 inch-pounds. The y in the formula is the distance from the beam center to the very bottom, which is just half the height, so 9 inches. So we take 300,000 times 9 and divide the whole thing by the Ig we just found, 5832. And that tells us the stress is 463 psi. And here we go. This is the showdown. The stress we're putting on the beam is 463 psi. But what's the beam's actual strength? Well, we use that modulus of rupture formula, and it tells us the concrete can handle 474 psi. So, 463 is less than 474. The beam holds. It hasn't cracked. We're still in the safe zone. Okay, so 25-foot kips wasn't enough. But how close were we? Let's find the exact breaking point. We bring out our main formula. MCR equals Fr times Ig divided by Yt. We know all these numbers now. The strength, Fr, is 474. The inertia, Ig, is 583.12. And Yt, the distance to the bottom, is 9 inches. You plug all that in, do the math, and you get 307,152 inch-pounds. Convert that back to the units we started with, and there's our answer. The absolute limit for this beam is 25.6-foot kips. Just a little bit more than we tested.
So, a rectangle is nice and easy, right? But in the real world, beams come in all sorts of shapes. Let's level up and tackle a T-beam. The rules are the same, but you're about to see how the geometry makes the math, well, a little more interesting.
So check this out. We've got this T-beam. It's got a big, wide 60-inch flange on top and a skinnier 12-inch web on the bottom. The concrete is a little different, 3,000 psi this time, and we're going to hit it with a much bigger force, an 80-foot kip moment.
Now, with a shake like this, it's not symmetrical top to bottom. So the first thing we have to do is find its center of gravity, what we call the neutral axis.
That big formula you're seeing, it looks intimidating, but it's really just a fancy way of finding the balance point between that big top part and this skinny bottom part. Once we run all the numbers, we find that balance point. The neutral axis, y bar, is 10.81 inches down from the top.
And wow, here's where the math really ramps up. To get the moment of inertia, IG, for this shape, we have to use something called the parallel axis theorem. Basically, we calculate the inertia for the top piece and the bottom piece on their own, and then we add them together along with a correction for how far away they are from that neutral axis we just found. It's a beast of a calculation for sure, but look at the result. 60,185 inches to the fourth? That's way bigger than the rectangle, which tells you this T-shape is way more resistant to bending.
Okay, we have our iGEM, so let's go ahead and find the cracking moment for this T-beam. But stick with me here. After we do that, we're going to do a little experiment. Something simple, but with a pretty surprising result.
All right, let's run the numbers. First, we need the concrete strength, the FR. For 3,000 psi concrete, that comes out to 411 psi. Next, we need YT, the distance from our neutral axis all the way to the bottom. So we take the total height, 32 inches, and subtract that 10.81 inches we found earlier. That leaves us with 21.19 inches. We plug everything into our cracking moment formula, and we get a cracking moment of 97.28 foot kips. Remember that number.
So, 97.28 foot kips. That's its limit. But what if we did something really simple? What if we just took the beam and flipped it completely upside down?
The result is kind of mind-blowing. Look at this. The beam's internal properties, its neutral axis, its moment of inertia, they don't change at all. It's the same beam. But YT, the distance to the bottom fiber where tension is highest, is now only 10.81 inches. We plug that one new number into our formula, and the cracking moment shoots up to almost 191 foot kips. It's nearly double the strength just from flipping it over. It just goes to show you, orientation is everything.
Okay, so we've been deep in the weeds with calculations for rectangles and T-beams. Let's pull back for a second and look at the big picture. Why do we care so much about this one specific moment? The moment of the first crack.
So, here's what it all comes down to. That cracking moment, McRae, it's the line in the sand. It's the end of the line for the concrete acting as a simple, uncracked block. And we've seen that this limit comes down to two key things: how strong the material is and the shape of the beam. And man, did we see how much shape matters with that T-beam. Knowing this number isn't just for fun. It's the absolute first step you have to take to design concrete that's actually safe and reliable.
So we figured out how to predict that first crack. But that just leads to more questions, doesn't it? I mean, what happens after the crack? The beam doesn't just fall apart. So how is it still holding up? And what about all that steel inside? What's its job in all of this? Well, that, my friends, is where the real story of reinforced concrete kicks in.